Okay, so now we got some math. It's not that bad. So we have Ohm's law, and what Ohm's law represents is the relationship between volts, amps, and ohms. There is a relationship with them. And see that little circle? You should get it tattooed on the back of your hand. That little circle is your cheat sheet for how this all plays out. So what Ohm's law says is that 1 volt equals 1 amp times 1 ohm. Okay, the formula can be expressed by a few different things based on what that says. So what happens here is we have a circle. E is volts, I is current, R is resistance. EIR. All right, you draw your circle, you to E at the top, a line across, a line down, I and R across the two sides. Now what we do is we cover whatever we want to find, and we do the math of whatever's left. So if we take this, and we have our circle like this, we put our hand over what we want. Let's say we want to know what volts are, but we know the current and the resistance. Voltage equals current times resistance. If we want to know current, we block that one. Current equals voltage divided by resistance. If we want to know resistance, we block that one. And now resistance equals voltage divided by current. Excuse me. That is everything that this says here. Okay? So all you need to do is block whatever it is and do the math of whatever's showing. That will get you out of trouble. So we have two different kinds of current. We have direct current, which is produced by a battery. Current flows in one direction. A battery is never negative 12 volts. It's either voltage or zero. Never the other way. Therefore, everything that's battery related or computer related is direct current, DC. Alternating current is produced anytime a conductor moves through a magnetic field. Current changes direction from positive to negative. If we take our meter and we stick it in the outlet, which we will one day, maybe I'll show it to you in a video, we see that we have current that's coming out of it, and you'll measure 122 volts, something like that. We take the leads, we switch them, we stick it back in, we still have 122 volts. Okay, because we are constantly, we have a generating station and a power plant, and that generating station has magnets in generators that are spinning and spinning. So as a result, we have this sine wave that develops as our north and our south poles line up and switch, and south to north and back and forth. Okay, this is what comes from anything that has a magnet involved with it. To have a circuit, we have components that we have to have in it. We need a battery, right? We need a power supply. We need wires to connect our pathways, and we need a load of some kind, a resistance of some sort, a light, a motor, a resistor, something like that. What's good to have is a switch, because naturally, if you don't have a switch, it stays on and kills your battery. We need circuit protection, and this is a symbol for a fuse. We want that close to our power source, and that protects it in case the amperage gets too high. That will blow instead of melting our circuit. If this switch is closed, that is a closed circuit, right? There's a pathway. An open circuit would be an opening where we don't have a complete one. The switch could be open, the fuse could be removed or blown, the light bulb can be out, or the battery can be disconnected on one side or the other. Okay? Those are the ways we can have an open circuit. Naturally, if you take a pair of cutting pliers and you cut the wire, it's open too. So we have a relationship that is always there. Nature made it this way. When a current flows through a conductor, there's a magnetic field that's formed around the conductor. I'll show that to you in a video. When a conductor is passed through a magnetic field, electrons will flow. So it's a two-way street. Current flows, we get a magnetic field. We move something through a magnetic field, electrons flow. It happens all the time. That's the principles that our alternators work on, our electric motors work on, relays work on, all that stuff. So now we have some factors that affect the strength of an electromagnetic coil. See, I don't know if you've heard me talk about windings, right? In every solenoid, motor, anything we have, relay, we have a winding. And that's a winding that's wrapped around and 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 around, usually wrapped around an iron core. What happens is we have a magnetic field that forms around that wire as current runs through. But when we coil them together, those magnetic fields overlap each other. And when they do, we become bigger. Now we run current through it, and it gets even bigger, right? Just like the electromagnets you see in the junkyard that pick cars up and then drop them. So there's some things that happen here. The amount of current flowing through the wire decides how magnetic things get, how strong it gets. And if you look over here, you can see that 1 amp flowing through 1,000 turns of wire is the same as 10 amps flowing through 100 turns. So the more amperage that flow through it, the bigger the magnetic field gets. The number of windings or turns. If we wrap those wires around and that magnetic field is going through that wire, then the more times we go around, the stronger that magnetic field gets, because that magnetic field is overlapping more and more and more. The size and length and type of core material. We usually use an iron core down the middle of this, but if we had a different kind of metal, that magnetic field might not be as big. And then the direction of the magnetic field at which the lines of force are cut. It all depends how the magnetic field, the way the field surrounding the wires. Right? There's a relationship that comes with the direction that the magnet faces and that kind of stuff, and that's what that comes into. We're not going to go too crazy into it now. You just need to get a feel for these principles that are at play, because when you drive your car home later, these things are happening. And finally, our last thing. This is the theory of induction. Electricity can be produced by magnetic induction. If we have an ignition coil, every ignition coil has a primary and a secondary coil. Okay, 2 sets of windings. We take the primary windings and we run current through them. They develop a magnetic field. The secondary coil, the secondary windings, are next to it. They're not part of it. They are next to it. Well, remember before we said, well, if we take and we run current through a conductor, we get a magnetic field. Or if we move a conductor through a magnetic field, we get current. So here, because those things are next to each other, the current that is formed in the one set of windings overlaps the secondary windings. Now the electrons start flowing in those secondary windings because they're in a magnetic field. Okay, that's induction. And there is your electrical theory for this week, right? Go over anything that you don't understand, ask questions or do research, and make sure you understand it. Everything will build upon these rules that are here. When you take 141 and you take electrical, it will come to you easier if you make peace with this stuff now.